Yeah, I handed back that functions quiz yesterday. It's pretty solid. It's mostly A's, couple B's and C's here and there. When we break out and start working on something else today, I can cruise around and check in with people who got B's or C's just to make sure they're good on whatever they missed and got wrong. I gotta say I was very excited to work with you guys yesterday. You guys are sharp, and I think we're gonna rock and roll through some calculus. But before we jump into it, I just want to ask y'all a couple questions. When I say y'all, I mean Cecilia. What did you take away from yesterday? What was one thing that you got from yesterday? Could have been anything. Yes. You guys are all very smart. Excellent. How about Mary? Any thoughts about yesterday?
I like how you're telling us like how people when we go to classes, people are always like, "Oh, what are we gonna use math for?" You know, like you're telling us. I like how you're like just excited about it.
Yeah, good. I feel like my philosophy at the school I teach at is if I'm not stoked about teaching a thing, y'all ain't gonna be stoked about learning that thing, right? So I try to only bring things to my students that I can talk about with conviction and passion, enthusiasm, and say that there's actually some kind of meaning or use for this thing. Otherwise, there's no buy-in from students, right? Students are like, what are you talking about? So yeah, I strive to do that, and thank you for picking up on that. Leslie, what else about yesterday?
I think giving jokes to keep our attention on the next night.
Okay, cool. Yeah, I try to do that too. Because math is, guess what? Math is dry and boring sometimes. And sometimes it's just a grind of just solving equations and formulas. And it can be boring, and it can be traumatic for a lot of people. I think math is the first subject that any child ever says the word can't, right? It just at some grade, I don't know when it is, but it just hits people, and they're just like, oh man, this sucks, and they start giving up. And I think it's when early on math is like, there's 3 apples and plus 5 apples, and then it's like, oh, there's clearly 8 apples. But then we start using all these symbols and getting into abstract concepts and stuff, and people just, there's this split from reality. We're like, what is this stuff we're learning? What does it have to do with reality? Right? And if it's not related to reality, people are like, why am I learning this? This is stupid. And they give up. So I try to connect it with, like I said, hey, this is a parabola, right? Like there's math everywhere. Math is the language of the universe. And so it's neat to speak that language. Anyway, Alessandra, any other thoughts about yesterday? No? Okay.
I enjoyed it.
Cool.
It was easy.
Nice.
Understand, like your teaching style.
Cool.
Like even though it was just review, I'm
Mhm.
assuming that would transfer to what
Right. Right, absolutely. Cool, yeah, but we didn't really teach new material yesterday. But, I need to gauge where everyone's at. And so, today, we're going to jump into rational functions. And let me explain. You might be like, ooh, rational functions. I know this already. But rational functions, it's going to be different than yesterday because it gives me, there's an opportunity to do algebra when you're dealing with rational functions. So I'm going to get an assessment of how you all are with factoring and multiplying and canceling, simplifying. So we'll get a little bit of algebra skill today, where I'll get to see where you are algebraically. And also, rational functions, they're weird functions, right? Like if you see a quadratic, you know the shape of it. It's going to be a U shape. But a rational function, they're bananas. You never know what's going to happen. So there's divide by zeros and there's asymptotes and things flying sideways and crazy. Like you don't even know what's going to happen. But in rational functions, more so than in anywhere else that I can think of, is you see a direct relationship between the equation and the graph, right? So, like log of x, right? We said the graph looks like this. There's nothing about this equation that implies this, except for the fact that you memorized that a log looks like this. Or there's nothing algebraically, numerically that suggests that. But in rational functions, we can look at it and say, where's the denominator equal to 0? Right? We're going to have either a whole or vertical asymptote. Where's the numerator equal to 0? That's going to be a 0, x-intercept. And we can visualize it based on the numbers and the variables and the algebra of the equation. And so it's a good place to go as we're leading into calculus. And it's also the beginning of the foundation of calculus is limits. Does anyone know anything about limits? Okay. Okay. Cool. Yeah, limits. That's key. That's the foundation. That's what sets apart calculus as a whole different ballgame from all the other math you've ever seen. Limits are a really slick idea, and so rational functions are going to get us ready for this limit stuff. So let's see how you guys are doing with rational functions. So a rational function. Let's see if I'll just ask anybody. A rational function is a blank divided by a blank. Did anyone complete that? My man, right here. Yeah, it's a polynomial function divided by another polynomial function. So it can be a cubic divided by a linear, quadratic over a quadratic, anything like that. And a very simple one. We should talk about Al real quick. I love this dude. Have you guys seen this quote? Albert Einstein. He said, "I have no special talents. I'm not some guy harder than you, better than you, some type of genius. None of that. He said, I'm just passionately curious." I love that. Right? And this is what I was telling you about yesterday about asking questions. When you ask questions, smart people ask questions, and that's what this guy did. He wasn't satisfied with just the way things were, right? And all of the brilliant minds are people who question things, like throughout history, right? Because who was the old head? Aristotle. He said, "Heavy things fall faster than lighter things," right? Which is not true. But Aristotle said that, BC. And 400 BC, something like that, and people believed it for 2,000 years. 2,000 years, people were like, "Yo, Aristotle said that. He's right about everything," and no one questioned it. And all you had to do was take two objects of different weight and drop them. This is my blood tester. Maybe I shouldn't be dropping that. That's like crucial. My existence. Well, there's a little air resistance happening here, but we'll see. Oh my God! They fell at the same speed, right? It took 2,000 years for someone to do that and say, "Oh, maybe he was wrong," right? And that dude was Galileo, and Galileo was the first cat that said, "Hey, why don't we do experiments to verify stuff instead of just all the Greeks were just like wearing togas and eating grapes and like coming up with theories and stuff." And they weren't actually doing science. So Galileo was like, let's do actual experiments and test things. And he started questioning everything. And when you question stuff at that time, around the Renaissance, you start asking questions and people want you dead. It was a scary time to be asking questions. But Galileo was a gangster for sure. And so he pulled it off. But anyway, anyone who ever did anything great was someone who questioned. And we're just curious, and we're not satisfied with someone just saying, "Well, just because," right? So I hate to say it, but when you guys say, "When am I ever going to use this?" Like, that's a good question. Even though I'm sure it pisses off every math teacher in the world when you ask that, but it's a natural question, and that's why everyone has it, because you guys are curious, right? And a lot of students, it's unfortunate, a lot of students, little baby kids come into the school system and they're like little question marks. kids, they're just little question marks. Why? It's just a little question mark. And the school systems, a lot of the school systems, unfortunately, turn kids into periods. Right? Like, here's the fact. Shut up. And I want you guys to stay curious. Right? Question everything. Why? Anyway, okay, I'm preaching. Rational functions. Let's get it. So let's say, I don't know, that's a rational function. Oh yeah, we have blue sleeve, we have graph paper, we have one more blue book. If anyone spills coffee on our blue book.
Or water.
Yeah. Oh no. Let's. So, a rational function, this is kind of a simple one. We're going to look at some different things about this rational function. We're going to look at points of discontinuity, vertical asymptotes, holes, and then we'll look at the domain, the zeros, if any. Then we will take a look at the degree of the upper polynomial. We'll compare the degree of the lower polynomial and the upper. We'll look at the lead coefficients of the top and bottom. And then we'll find out whether or not there's a horizontal asymptote. Right? So we can pull all this information just by looking at this equation, right? And so that's what I'm telling you, it's different than like log of x. We can see some neat stuff happening. So what is the point of discontinuity?
3.
Oh, okay. X equals 3. Yeah, but what does it mean though?
When x equals that number, it's undefined, where f of x is undefined. So
Nice.
It's like a whole.
Yeah, there's something where you're drawing your graph and you have to pick up your pencil and like continue somewhere else, right? It's discontinuous. So it's a point of discontinuity, and every point of discontinuity, we're going to say it is either a vertical asymptote or it's a hole. So we got to decide which one of these things x equals 3 is. And I just talked to you. Selena, how do you know which one? Vertical asymptote or a hole? How do you know? Okay, does anyone remember that? Heather?
I try to guess because it's a linear function. It would be a whole.
No.
If there's x minus 3 on top, then you could cancel it out. You multiply by 5 though.
If there's an x minus 3 in the top and then these canceled, they call it a removable discontinuity. Have you heard that? A removable discontinuity is a hole. And since there is no such thing, and this is an essential discontinuity, because you can't remove it, you can't simplify it out, essential discontinuities necessarily will be vertical asymptotes. So that means that this x equals 3 is a vertical asymptotes goats, and there is no hole in this function. Is that okay? Did I explain that? Maybe I should say vertical asymptotes. So let's see. So point of discontinuity is a hole if it cancels on top and bottom. And it is a vertical asymptote. Can I write VA? Vertical asymptote? Okay. I'm going to write that all out. Vertical asymptote, otherwise. If it does not cancel. Right? And again, they call this removable. Because you can remove it. You can cancel that thing out. Removable discontinuity. And this thing is called an essential discontinuity. Alright, cool. I feel like I'm actually teaching you something. We good? Now remember, I want you guys to ask questions. So ask questions. Daphne.
If otherwise worded. What do you mean by that?
Oh, if it doesn't cancel. Yeah. Okay. Thank you. I try to be all shorthand and slick, but thank you. If it does not cancel, you cannot simplify it. So this x minus 3, there's nothing we can do algebraically to make that x minus 3 go away. It's essentially there. We can't simplify, cancel, make it go away. Cool? Thank you. So the domain, what are the possible values that x can take for this function? What the domain for this function, Gina, will be what? Yeah, so we'll call it all real numbers not equal to 3. Is that cool?
Yeah.
And then zeros, so points of discontinuity, these all happen when the denominator is 0. Because if the denominator is 0, you try to divide by 0, and that's not a thing. Right? You guys clear on that? Your parents tell you don't try to divide by 0? Like don't play with matches, stuff like that. It's just bad. Don't do it. But it's not possible. So we need to safeguard against dividing by 0 because when that happens, it's undefined and we don't know what's going on there. So that's discontinuity, divide by 0. Make disconnections. When we divide by 0, we have discontinuity. Now, when the numerator is equal to 0, then you have 0 divided by, some stuff or whatever. You have, who cares? 0 divided by anything is 0, right? So you can't divide by 0, but you can have 0 divided by stuff, right? Like, I'm going to buy 0 pizzas for y'all today at lunch, and then we're going to divide them up evenly. Everybody gets about 0 slices. Okay? So when the numerator is 0, the whole function equals 0, and that's where your x-intercepts will be. These are the places where the numerator equals 0. So, Hele, when does this numerator equal 0?
Never.
Yeah. When does 5 equal 0? That doesn't happen. So there's no zeros. None. Cool. Now, comparing the degrees, do you guys know what I mean when I say degree? The degree of a polynomial is like the highest exponent in that whole polynomial. So the degree, Mary, what's the degree of the bottom polynomial?
Before that, what did you say before? About degree?
About degree. Degree is the highest exponent. So a quadratic is 3x squared plus blah, blah, blah. The degree is 2, because x to the 2 is the highest exponent, right? So what is the degree of the denominator? 1. And so, therefore, what is the degree of the numerator?
0.
Right, x to the 0,
Okay.
right? So this is, it sounds ridiculous, but this is like a 0th degree polynomial, kind of. Okay, the lead coefficients, Janice, lead coefficients for the top and the bottom, what do you think?
5.
The top is 5.
1.
Yes, ma'am. So the lead coefficient is, if you have 5x squared minus 6x cubed plus 8. The lead coefficient is you find the leading term, the thing with the highest exponent. That's the boss right there. You talk to the boss. And the lead coefficient is the thing in front of the boss. So -6 is the lead coefficient for this guy. And generally it's written in standard form with the highest exponent and then it descends. But sometimes, people want to be slick, throw a curveball at you. But anyway, so yeah, those are the lead coefficients. Are we good? Am I going too fast, too slow, too weird? We good? Okay. Mauricio, you know how to find horizontal asymptotes, don't you?
You plug in 0. Or you make it equal to 0.
I don't think so. I feel like that would find me a, when x equals 0, that would give me a y-intercept, right? So it's not very simple to find the horizontal asymptote.
Is that like,
I think it's 0.
if it's low, it's a higher graph.
Okay,
The degree on top is higher.
Christian's on to something. So to find the horizontal asymptote, you compare the degrees of the top and bottom. So if the top is larger than the bottom, then you have, for this, say you have like a x cubed plus 1 over 2x. And so horizontal asymptotes are talking about as you go to infinity or negative infinity. When you start plugging in really, really big numbers for x. So if I plug in, a million here, a million cubed is going to be way bigger than 2 million. Yeah, you follow me?
Yeah.
So the top is going to get huge way faster than the bottom is, and it's just going to go off to infinity. AKA, there's no horizontal asymptote. It's unbounded. It just goes off to infinity. So if the top of we're going to compare the degrees. We compare the degrees of our function, and if the top is greater than the bottom, then there's this is terrible how I'm doing this. If we're going to compare the degrees, and if this is bigger, then there's no horizontal asymptote. Now, if the bottom is larger than the top,
Isn't the
so let's think about it. If that's the case, and we have a function like this, where we have a cubic in the bottom, and so again, we're going to have a bajillion. We're going to have 2 million divided by a bajillion, right? Which is approximately what? It's it's getting really, really close to 0, because the denominator is going to get huge way faster than the top is. So it's going to level out at 0. So horizontal asymptote will be y equals 0. If that's the case. Make sense? Asia, we good? Okay. And now if they're equal, if the degrees of the top and the bottom are equal,
You take a linear coefficient.
yes, it's the horizontal asymptote will be a ratio of the lead coefficients. So check it out. We have a 2x cubed divided by x cubed plus 1. If I plug in a million, I have a million cubed plus 1. That plus 1 is silly, isn't it? So as x gets huge, for x approaching infinity, this plus 1 is small potatoes, and I don't even need to worry about it. See how that plus 1 is silly? Silly little thing. Right? And then check it out. I have x cubed divided by x cubed. This essentially cancels. And we're left with the lead coefficient in the bottom was 1. So we're left with just the ratio of the lead coefficients, 2 over 1. So if they have equal degrees, the horizontal asymptote will be y equals a ratio of the lead coefficients. Whew. So this is these are the 3 cases of how to find horizontal asymptotes. Fun times. So, who done it? Huey, what is the horizontal asymptote going to be for this function here?
0.
Yeah, y equals 0, right? Because the bottom is growing faster than the top. Cool. All right, I want to do another example. So, AKA, I want to erase this.
Yeah.
Can I erase this?
Yeah.
All right, that needs space. All right, let's do this one. Step our game up a little bit. 2x squared plus 6x plus 4 over x squared minus 1. A little bit harder. Whew. What's the first thing we should do with that, though? Any ideas? Yeah, let's factor it. It's kind of ugly. So, Asia, how would one factor that? Yeah, let's pull a 2 out. I'm gonna do it over here. So pull out a 2, and then what do we got? Now, Andrew, do you recognize this thing here?
Yeah, it's the difference between 2 squared.
Yes, sir. So how do we factor that?
Be x plus 1 times x minus 1.
Oh man, sounds good. And then we could actually factor the top further. Christian, you got this.
X plus 2, x plus 1.
Oh my man, x plus 2, x plus 1. You guys see it?
Yeah.
Let me write it here. 2 x plus 2 x plus 1 all over x minus 1 x plus 1. What do you see? Yeah, we can cancel that thing. Now I'm not going to cancel it just yet because first we're going to talk about the points of discontinuity and whatnot. So Daphne, where are my points of discontinuity?
1.
Mm-hmm. I'm sorry, say it again.
1 and 2.
No. So PODs, we're looking at the denominator only. Don't even worry about it. Yeah, wherever we divide by 0, that's where bad things happen to good people. So 1 and negative 1. Those are bad. You stay away from those. Bad. And then Stephanie is not here. So I made it through my whole stack already. Yeah. Start over. Janice, do we have any vertical asymptotes? Right, we need to determine, we definitely have 2 PODs, and we need to know if they're holes or vertical asymptotes.
Does cancel? No.
So this cancels. So what does that mean? What's a hole? So this is the factor x plus 1, but the value for x would be negative 1, right? So when x equals negative 1, we have a hole. And this one does not cancel. What does that mean? Yes. When x is 1, we have a vertical asymptote. And then the domain for that thing, Jack, is what?
Domain, that would be negative infinity. Oh.
Yeah. Let's just say that.
I love the interval notation.
Yeah, I know you love that interval notation. Yes, Andrew.
Okay, so when you get your problem, right, you factor out first.
Mhm.
Before you start canceling things, you check if it's a hole for the holes in vertical asymptotes.
Yes.
Okay.
Absolutely. Yeah. Good question. All right. Zeros, Gina. X equals -2 for sure. Now x equals -1 is a discontinuity. So even if it was at 0, we know it's a hole. Right? So yeah, so not that one. That one doesn't count. And then Alessandra, the degree of the top and bottom.
2/2.
I think so. Yeah, 2/2. Lead coefficients, Cecilia?
2.
Two over what? Well, the bottom has a lead coefficient, has to. No. If the lead coefficient was 0, it would decimate the whole village. Right, that's not cool. Yes, it would be 1. Okay. 1. And then so the top is no. What's going on with the horizontal asymptotes here, Selena? What's the thing?
Well, the top is equal to the bottom.
Mm-hmm.
So we're just going to lead coefficient of the first one and lead coefficient of that one.
Which is what?
1. Well, it's like 2 over 2.
No, these are the degrees. Lead coefficients.
Oh, 2 over 1.
Yeah. So y equals 2. You know what we should graph the first ones that we've done. And these graphs are crazy. But how are we doing? We good so far? Okay, let's try graphing this first one. So the first one, we have a vertical asymptote at 3. X equals 3. I'm going to just draw a dotted line here first. And what else? We have no zeros. Oh, we have a horizontal asymptote at y equals 0. So that's here right on the axis. And then these rational functions, they more or less look like this, right? They approach asymptotes because that's what they do, right? Asymptotes are things that you approach. Yeah, and it kind of looks like that. Ballpark. My y-intercept is probably wrong, but I'm just drawing the general shape of it. Yeah, is that okay? The second one, let's graph this second one. 1, 2, 3, 4. The second guy, what can I put on the graph here? We have
Line on 1.
yeah, vertical asymptote at x equals 1. Yeah, okay. I can't put the hole there because I don't know where to put it yet.
Plug it in.
What else can we put? We got a horizontal dude, right?
Yeah.
Yeah.
Y equals 2. So y equals 2, we got a horizontal here. Do we have a 0? Yeah, we do have a 0 at -2. X equals -2 here. It's going to be a 0. So I'm guessing that this thing is going to be a similar shape. It'll be one of these guys. And something like this, except where's that hole? At x equals negative 1?
-1.
So at negative 1,
It's negative
we got a little hole in the graph. And you won't see it when you graph it on your calculator, just because of pixels and things. Like the calculator isn't able to show it. But if you trace the values on your calculator, you guys know what I'm talking about? The trace function on your calculator, you can type in x equals negative 1 and it'll say y equals, and it won't tell you anything. Just keep seeing it. So yeah, this is the graph, more or less. Have you guys have done this kind of stuff?
Yeah.
Yeah. Okay. They're crazy graphs, right? They're preposterous, and sometimes you'll get a bunch of different. We'll do one more example, and we'll try to run through it real faster. I feel like I'm talking all day. Let's do another one. Okay. H of x is x cubed plus 2x squared minus 3x, x squared plus 3x minus 4. Okay, Mauricio, what are we gonna do? Step 1.
Back to the top.
Yeah, let's do that there.
X.
Yeah, let's pull the x out.
Times X.
So x squared plus 2x minus 3. Can you factor the bottom?
Yeah.
What's that?
X plus 4. X plus 1 and X. No, it's X plus 4 and X minus 1. Right.
Okay. Yeah, x minus 1. X plus 4. Does that work? Is he good? Yeah? And then we could probably factor this top real quick. Right. Daphne, can you factor this trinomial here?
X plus 1.
Mm-hmm. Maybe, I don't know.
X plus 1, and then x minus 1.
Plus 1 minus 1? That's suspect. I'm not sure about that.
Minus 3.
Yeah.
Plus 3.
Plus 2?
Plus 3.
Plus 3 minus 1?
Yeah.
Daphne, is that right? Plus 3. So remember, these things need to multiply to make your last term, negative 3. And they need to add to make your middle dude, which is 2. That checks out. Yeah? Okay. Oh, I see some cancel-y things. Ooh, yeah.
Oh no.
Sweet. But even before, so we'll still pretend that these are there when we discuss points of discontinuity. So Leslie, PODs.
X plus 1 and X minus 1.
Yes. X is when x is equal to 1 and when x is equal to negative 4. Those are places where the denominator is bad. Bad denominator. Hele. Break it down on which one is a whole, which one's a vertical asymptote.
X equals 1 is the whole, and X equals negative 4 is the vertical asymptote.
X equals 1 is a whole. X equals negative 4, vertical asymptote. Cool, we're moving. Mary, what's the domain on that?
All real numbers except for 1 and negative 4.
1 and negative 4. Sweet. And then Asia, zeros. X equals negative 3. Any other zeros? Yes. right? Because we have this guy out here. If we plug in a 0, -3 and 0, those are the places. Huey, what are the degrees in the top and bottom?
3/2.
3/2. Andrew, what are the lead coefficients?
Oh wait, never mind. We're both. 1 and 1.
Yep. You guys know why? Think about it. If you multiply all this junk out, right, like you FOIL this, you're going to get x times x is x squared. And you're going to multiply by x, and you're going to have x cubed. But x times x times x, that's x cubed. It's 1x cubed. Right, and that's going to be your lead coefficient. And same thing down here, x times x. That's going to give you your 1x cubed. And all the other stuff, who cares? So it's going to be 1/1 for your lead coefficients. And so now, Johnny's horizontal asymptote, what's it going to be? I don't know.
None.
Y is equal to 0.
The top is growing faster than the bottom.
Y equal NA.
When they're equal, so check it out. So here we compare these to see which case is it, and if the top is bigger or the bottom is bigger, or if they're equal degrees. We compare these, and if they have equal degrees, then we use the lead coefficients. If the bottom is bigger, it's automatically 0. If the top is bigger, it's automatically correct. There's none. Because this is just going to approach infinity. And so graphing that, I would regraph that. It might be ugly. Let's try. Yes, sir.
So isn't there, if there's no horizontal asymptote, wouldn't there be a slant asymptote?
There could be a slant asymptote, yes. This guy. How many people know about slant asymptotes? Oh, you guys are nerds, man. I love you guys. How do you find a slant asymptote?
You actually divide it out.
Yeah, you have to do polynomial division, my favorite. So yeah, you have to divide it, and you get a thing, and then there's a remainder, and your remainder is the slant asymptote. You want to do that?
Yeah.
I was just asking. I didn't want to really do it. Let's do it. Let's go for it. Let me see what the original function was. There. Good. Good thinking, Christian. So if we want to find the slant asymptote, which is a thing, we got to do the division. So x cubed plus 2x squared minus 3x. Because remember, I can't divide when it's in factor form. Like I can't do long division. So we're going to divide that by x squared plus 6x plus 5. Can I use synthetic division?
Yeah.
No,
Sure can't.
because it's not mono.
Yeah, it needs to be linear. You can only do synthetic division if it's like x plus 5 is your divisor. So the way I do this is I look at the leading terms and I divide them. X cubed divided by x squared is what? X. So I'm going to put that here. Now I'm going to multiply this out. I'm going to get x cubed plus 6x squared plus 5x. I'm going to subtract all that. Bring it down. That cancels on purpose. 2 minus 6, negative 4x squared. Negative 3 minus 5.
I don't think that's the original equation.
X squared plus 3x minus 4 and
Did I mess up? I messed up.
Which one we do?
Yeah, I wrote the wrong thing. Look at you paying attention and stuff. What was I writing? X squared plus 3x minus 4? Is that right?
yeah.
Nice, you gotta keep me in check. get crazy. Okay, same lead stuff though. So, okay, we're okay here. But yeah, let's do this again. X cubed plus 3x squared minus 4x. And then I'm going to subtract it. So minus, minus. This becomes a plus. This cancels. 2 minus 3, negative 1x squared. Negative 3 plus 4 plus 1x. There's nothing else to bring down. And then we do the same thing again. We look at the lead stuff. We say how many times does negative x squared, or how many times does x squared go into negative x squared? Negative 1 time. And then we do this thing again. Negative 1, negative 3